Okay, now I want to talk a little bit more about electric fields and about capacitors. A capacitor is a device for storing electric charge, and it can also create a uniform electric field. In this book, we talk a lot about parallel plate capacitors. And a parallel plate capacitor is simply two pieces of metal that are next to each other. And we call it a parallel plate capacitor because we envision them as two plates that are parallel to each other, kind of like that, like two sheets of paper almost, like this. Of course, they have to be conductors, so you couldn't make a capacitor out of a sheet of paper. A capacitor is just two conductors hanging out next to each other. Here's a couple of examples of real-world capacitors. This is an old school capacitor that I tore out of an old electronic device that I bought on eBay, and it's adjustable. So by turning this, I can change its capacitance, and it really is just a bunch of metal plates, though, that interleave. And so it really is just parallel metal plates, which you can adjust how much of them overlap. So that's a capacitor. You could store charge. You could create a uniform electric field with that. These are some more realistic or more modern capacitors, I guess. I like to build guitar amps. These are all different types of capacitors that might go in an electric guitar amp. I've taken one of these and unrolled it, and it is, we'll show these again in the next chapter. When I unroll this, you can see that it's just two pieces of foil with an insulating layer in between. So it's not quite a parallel plate, but you can imagine that if you unrolled this whole thing, it would be like two very long parallel plates. Here's a more modern device. This is not out of a guitar amp, but a different kind of a capacitor. So anyway, that's what we're talking about when we talk about capacitors. And exactly what their role is in a circuit, we're going to spend a lot of time talking about that here in a chapter or two. Looking at this PowerPoint, a parallel plate capacitor is an arrangement of two electrodes. What's an electrode? It's just a conductor. Two pieces of metal. It would be nicer if they just said that. Two pieces of metal closely spaced and charged equally but oppositely. So we've got a negative charge on one plate and a positive charge on the other plate. An electrode is just a conducting plate, as I said. If we look at sort of a cross-sectional view here, we see why it's called a parallel plate. These two plates are parallel and they're separated by some gap. Now, we know that those negatives in the top plate and those positives in the bottom plate, they really want to get to each other. There's a strong attractive force between them, which is why this also stores energy. So it stores charge, it creates a uniform electric field, and it also stores energy. So if we were to look just a little bit more at the electric field on the inside of that capacitor, we know that electric fields always point from positive to negative. And the nice thing about the parallel plate capacitor is it creates a uniform electric field. It is the same everywhere. And we have an equation for what it is. The electric field in a capacitor is the charge on one of the plates, or both of the plates, right? They are equal and opposite. So it's the charge on each of the plates, I should say, divided by epsilon naught A. A will come right back to. Epsilon naught is a constant. And it's related to K. Remember K from previous sections, 9 times 10 to the 9th newtons, meter squared per coulomb squared. Epsilon naught is just, they're the same, right? It's just 1 over 4 pi times K gives us epsilon naught. We don't even need both of them. But for historical reasons and because physicists don't like to write 4 pi when they don't have to, we have both of them. Okay, so there it is. It's just a constant. Now what is A? A is the area of one of the plates. Again, going back to this drawing, we see that each plate has area A, and that's what goes in here. And so we can just calculate the electric field inside a capacitor. It's a fairly straightforward calculation. The real point is we get a nice uniform electric field due to a parallel plate capacitor. Now, what about another arrangement? What if we were to put a positive and a negative next to each other? This is a very important situation that shows up all the time. And we call this a dipole arrangement. This is a dipole arrangement. Equal and opposite charges separated by some distance is a dipole. And if we were to look at the electric field at various points around this dipole, ooh, it's chaotic, isn't it? I don't really get a sense of the electric field by looking at these arrows. I don't know. These are the electric field vectors at each point in space. But if I sketch the electric field lines, which, if you'll recall, always start on positives, end on negatives, then we can get a sense of what the electric field due to a dipole looks like. And indeed, oh, this is so much more satisfying of an image. I can really visualize what the electric field looks like now. Again, recall, as I mentioned in a previous lecture, the electric field at any one point will always be tangent to the electric field lines that goes through that point. So, for example, to find this right here, we would find the tangent to this field line right here. Start on positives, end on negatives. Don't forget that the density of the field lines is proportional to the electric field strength. And so here we see that the electric field is quite strong in here close to the charge, and as I get farther out, it gets weaker. Quite strong close to the charge, weaker as I go out. Another little detail here, it's kind of hard to see in this picture. These should all be leaving at right angles. They are leaving the charges at right angles. We'll find that that is a rule for conductors as well. Here's a quick question. A set of electric field lines is directed as shown below. Well, at which of the noted points is the magnitude of the field the greatest? Why don't you pause the recording, give it some thought, and I'll be right back. Welcome back. What do we think? Well, remember that the density of the electric field lines is proportional to the electric field strength. And so here at D, I see the lines are the most spread out. So I feel like the electric field is weakest at D, and it is strongest at A, because at A, the electric field lines are closest together. And PowerPoint agrees. Yes. Moving along, rules for conductors and electric fields. Here we see a conductor. The electric field inside the conductor is always 0. And all excess charge will reside on the surface. It's just kind of a rule to remember. Why is the electric field inside the conductor 0? Well, remember that we are dealing with electrostatics. We're dealing with charges that are not moving. And also remember that in a conductor, charges are free to move. And also remember that electric fields exert forces on charges. So, if there was an electric field in a conductor, then it would exert a force on a charge. That charge would then move, which means we're not in electrostatics. When would it quit moving? It would quit moving until it arranged itself such that there was no longer a net force on it. When would that happen? When there's no electric field. So it just has to be, right? If we believe that conductors are objects where charges can freely move about as they wish, then the electric field inside that conductor just has to be 0. Why does the charge live on the surface? The charge lives on the surface because that is the very farthest that all of those positives can get away from each other. It's a complicated mathematical problem, but you can prove that if any one of these charges was in the middle here, then that would be closer to its neighbors than it has to be, right? If you've got a class full of really stinky people and no one wants to smell each other, then the best arrangement is for everyone to get along the perimeter as far away from each other as they can. That's a strange analogy. Take it for what it's worth. Okay. Same thing with a void inside a conductor. Inside a conductor, the electric field is 0. Electric field on the surface is always perpendicular to the surface. Again, if it had some angle to it, then it would drive the charges on the surface, put a force on them, and when they quit moving, then the electric field would be perpendicular. So, again, if we believe that a conductor is something where charges can move freely, then we have to also believe that the electric field will be perpendicular at the surface of a conductor. Perpendicular to the surface of the conductor, I should say. And also, along with that, charges tend to bunch up where the, if you've got a point or something like that on a conductor, which causes the electric field lines to bunch up there, indicating a stronger electric field at the point. Okay. Forces on charges in electric fields. Again, we really kind of already had this equation, though it was written a little bit different. Remember that if we know the electric field at some point in space, then there doesn't have to be a charge there to experience the force. But if we know the electric field there and we put a charge at that location, we know the charge, we know the electric field, we simply multiply them together, and that gives us the force. You'll recall that dividing this equation on both sides by Q was the way that we introduced the electric field. That we basically found the force on a particle, on a charge, and then divided away the charge, and what was left was the electric field. This is sort of the reverse of that. So, this is sort of what we call the field model of the force. Recall that in Coulomb's law, we said charge A affects charge B directly. We didn't care how that interaction happened. We didn't care about the fact that it was action at a distance. Now, in this model, we're saying, no, charge A creates a field at the location of B, and B interacts with that field and experiences a force because of that field. That's the model that's shown here. Notice that this is a vector equation, which means that if Q is positive, then the force is in the same direction as the electric field. Notice if Q is negative, the force is in the opposite direction as the electric field. It is a vector equation. Let's do a quick example. A housefly walking across a clean surface can accumulate a significant positive or negative charge. In one experiment, the largest positive charge observed was 73 picocoulombs. A typical housefly has a mass of 12 milligrams. Explain how a housefly could accumulate an electric charge by walking across a surface. Well, this is charging by rubbing. This is charging through friction. It's the same way that I charged up my PVC pipe. I rubbed it with my sweater, and some electrons were rubbed off of the PVC pipe or onto it, giving it a charge. In fact, in this case, the PVC pipe does acquire a negative charge. Indeed, when I rub my PVC pipe with the sweater, negative charges move off of the sweater and onto the PVC pipe, giving the sweater a positive charge and the PVC pipe a negative charge. But that's the idea. Through rubbing, I'm breaking away electrons and pulling them away from the object, leaving one positive, leaving one negative. Moving on to B. What magnitude and direction of electric field would be necessary to levitate a housefly with maximum charge? Well, levitate a housefly. That doesn't sound very physicsy. What does it mean? Levitate a housefly. It means, since the force of gravity is down, the question poses, can we exert an upward electric force which would balance that wake force and would make the fly float or levitate? So, a real physicsy way of saying this is, what magnitude and direction of electric field would balance the weight of the fly, or would be equal and opposite to the weight of the fly? Okay, let's start with the free body diagram. We know we've got the weight force down, and we've got the electric force up. The problem poses that we would like to levitate the fly. That's telling us that the electric force must equal the weight force. We know that the electric force can be written as Q times E, and the weight force is, of course, M times G. It's asking for the electric field strength, so we end up with electric field equals mg over q. And now we can plug in our numbers. We have a 12 milligram fly, so that is 12 times 10 to the negative 6 kilograms, times our good buddy G, that's 9.8, meters per second squared, divided by Q, which we were told was 73 picocoulombs. And we simply run our calculator, and we get an answer of 1.6 times 10 to the 6th newtons per coulomb. All right, 1.6 times 10 to the 6th newtons per coulomb. So that's our magnitude. What about the direction? Well, let's not forget our vector equation. That the force is equal to the charge times the electric field. And this is a vector equation. So, if Q is positive, E and F are in the same direction. If Q is negative, E and F are in opposite directions. In this case, we have a positive Q. That means the electric field and the force are in the same direction. If the force is up, the electric field must be up as well. Okay, so we got this number, 1.6 times 10 to the 6th newtons per coulomb. Is that a big field, a little field, in between? It's actually a pretty big field. And this piece of information in part C can help us to wrap our brain around that. So question C says, if the electric field in air exceeds about 3 times 10 to the 6th newtons per coulomb, the atoms in the air tear apart and the air becomes a conductor. Could the field you exist in, calculated in B, exist in air? Well, we see that this magnitude is less than this electric field that they've given us in C, and so the answer here is yes, it could exist. But notice that if it's much stronger, the air will tear apart and become a conductor. You've seen this happen. If you've ever shuffled your feet across the side, across the carpet, and then touched a doorknob and had a little zap, then you have seen this happen, because normally the air cannot conduct electricity. But when that electric field strength goes above this value, then the atoms literally get torn apart. The electrons go one way and the nuclei go the other way, right? They're opposite charged, so the forces are in opposite directions. It's called dielectric breakdown. And it's what happens when lightning strikes too. When lightning strikes, it actually pulls the atoms apart. And so the electrons go one way, the nuclei go the other way, and guess what you got to have air? Atoms. So when these atoms get torn apart, there's all of a sudden a hole in the atmosphere. And the air surrounding it fills in that gap in a real big hurry and creates a real loud sound called thunder. So you've actually experienced this. Okay, again, how big is this electric field? Well, pretty big, but you've experienced a field that's that big every time you have shocked yourself when you touched a doorknob after shuffling along the carpet.